Hello there, everyone. My name is Michael Chiappone, and I'm really excited today to take you on a deep dive into the world of sound. So, I'm a vertebrate paleontologist and naturalist with interests in anatomy, taphonomy, ecology, and bioacoustics. I'm currently working on a master's at the University of Minnesota, but I was born and raised across the various landscapes of Texas. Now, the reason I'm talking to you all today is that my undergrad research experience was in the evolution of vocalization and bioacoustics in birds. And this research really got me interested in animal sounds more generally and what soundscapes might have been like across deep time. So, what I'm going to do today is take you all through a primer of basic bioacoustics and why we study it, how animals produce sound, and what we know about sound production in deep time. I'm going to combine all of these in order to help you understand a little bit about how soundscapes have actually evolved through deep time. So let's go ahead and get into it. So bioacoustics is essentially just the study of sound production and reception in animals. Sounds are a major component of animal behaviors, and they can inform researchers about the diversity of life present in an ecosystem, even if you might not be able to immediately see every component of it. Recordings act as bioacoustic time capsules that capture a single moment in time, representing ecological conditions that right now are undergoing change due to human activity. This is also a major opportunity for citizen science, given that many people have microphones in their pocket at any given time. So, how do we actually represent sound in bioacoustics? Well, one of our main tools for that is the spectrogram. Spectrograms demonstrate two main characteristics of sound. First is frequency. Frequency is shown on the y-axis and is measured in hertz. This is the same as pitch. Intensity is shown here by the brightness of what we call these spectral traces. And the brightness essentially equates to volume. So that lowest note is called the fundamental frequency. This is the lowest primary frequency of sound present in a tonal sound. This is that green bar on the right there. Above those are harmonics. These are bands of sound spaced at even intervals equal to the fundamental frequency. So if the fundamental frequency is about 100 hertz, each harmonic would be spaced apart by another 100 hertz, 200, 300, 400, etc. Subharmonics come between harmonics, and they're typically spaced about halfway. Both of these contribute to the tonality of a sound, the quality of it. Chaos, on the other hand, is static, that is distributed across wide frequency bands, and is often associated with harsh sounds like hissing or vocal fry. Biphonation, which is shown on the far right, is actually the production of two separate sounds at the same time. This is common in songbirds, and we'll discuss that a bit more later. So what kinds of sounds can animals actually produce? Well, one of these is mechanical sounds. Now, these are sounds that aren't created through vibration of air using a dedicated internal vocal organ. This is things like stomping, drumming, tail slapping, bill clacking, rattling like this rattlesnake on the top right here, and many more. So, now I want to talk a little bit about the process of stridulation. Stridulation you may have heard of, and it's the process of creating sound by physically rubbing body parts together. This is done in several animal groups, like snakes or even mammals, like this tenrec, who is very bizarre.
They have a unique solution, specialized quills on their backs.
But among any animal, arthropods, like insects, crustaceans, and arachnids, are all famous for this. You can see this grig, a type of cricket, vocalizing here. Now, in insects, stridulation is often used as a mating call. and is done by rubbing their legs or wings together. Now, could we ever possibly detect this in the fossil record? Well, it turns out we can. As of these two recent papers by the same research group here, I've cited the most recent one, researchers have actually found extremely well-preserved specimens of Mesozoic katydid clades with wings and stridulatory structures preserved in 3 dimensions, which you can see on the right here. Because stridulation relies on no other soft tissues to produce sound, researchers used modern insects to model sound production in these Mesozoic specimens, probably to the most accurate degree that we possibly can, which is fascinating. So I'm going to show you that right now. This is from an animal from the mid-Jurassic. Now, you might notice that that sound is very high compared to what most people think about for katydids, and you wouldn't be wrong. What they found is that many of the specimens that they looked at from across the Mesozoic, but especially in the early part of the Mesozoic, we're talking Triassic and up to mid-Jurassic, many of these specimens were stridulating at really high frequencies compared to most extant crickets and bull crickets, which you can see their frequency range by that orange bar, ranging from about 2 to 8,000 hertz. These animals were not only vocalizing in that range, but also from 8,000 to over 16,000 hertz. Now, this tells us a few things. One, by even the late Triassic and beyond, katydid vocalization was already very diverse, even more diverse than it is today, which is fascinating. But not only this, because these vocalizations were already diverse by the late Triassic, a post-Permo-Triassic extinction world may have been welcomed in by songs of katydids filling the silence of a near-dead soundscape after that devastating extinction. It's thought that musical sound in katydids originated in the fairly early Triassic, so it didn't take long for them to take over the soundscape. Not only this, but this higher frequency range that you don't see in modern crickets and katydids is actually an acoustic frontier. None of the other animals in their ecosystems, like amphibians, reptiles, or early synapsids and such, could actually hear in these frequency ranges. You can see this for modern amphibians and reptiles. Their hearing ranges don't extend past around 8,000 hertz. This is fascinating because it means that these katydids were moving into unoccupied space and essentially having a radiation of diversity into these unoccupied spaces of sound instead of an anatomy, which is fascinating. This may have been a way to avoid predators hearing them and allowed them to sing at their leisure without fear of being attacked. Not only this, but turnover from extinct to extant katydid clades in the mid-Jurassic coincided with the diversification of modern mammal clades and extinct mammal clades. And importantly, vast improvements in mammal hearing capabilities, specifically increases in the frequencies at which they can hear. So that means that there's potential correlation here, suggesting a auditory arms race between predator and prey, which, if correct, is fascinating. All of this overall points to a very unfamiliar Jurassic soundscape. The insects would have sounded very different than what we have today. So let's go ahead and move on to vocalization via airflow and vibration. This is really what most people and what most researchers mean when they say vocalization. They mean vibration of air to create sound, typically in the respiratory tract of tetrapods. Now, you could argue that many of the things that we have already talked about are vocalization, but this is what is usually meant by that. Now, the outlier to this is fish. Fish use muscles attached to the swim bladder to vibrate air inside. And this is not something I'll be going too far into here, but if you want to hear some really fascinating fish sounds, you can go to fishsounds.net, which is a continuously updated database of vocalizing fish. Now, there are 2 main vocal organs in tetrapods, with a few exceptions. One of these is the larynx. Now, the larynx sits at the top of the trachea, which is composed of rings that stack leading down toward the lungs. The tracheal rings and the larynx itself are typically cartilaginous, although sometimes they are ossified in rare cases, such as with howler monkeys. Now, this is the primary vocal organ of many tetrapods. Mammals, reptiles, and amphibians all use this. What they do is they have membranous vocal folds of varying different shapes and sizes that they use to vibrate as air passes through and produces sound. You can see this on the top right for this mammal-style larynx there, how it can close the vocal folds and create tension and make them vibrate. Sounds exit through an open or closed mouth, i.e. out the nostrils, with differing results. Think humming versus singing. Now, despite what you might imagine for a cartilaginous structure, for the most part, we do actually have fossil evidence of larynxes in extinct animals. One of these is glyptodonts, specifically Panoptis. Panoptis has a larynx preserved, which bears striking similarities to pigs and especially California sea lions. However, this may be because we really don't have a great idea of what xenarthran tracheal anatomy looks like. And so we need more of that in order to compare to glyptodonts. On the other hand, we also have Oreodont larynxes, specifically this one from the late Miocene in Mexico. And this is the oldest mammal larynx known to date. In both of these cases, ossification seems to have helped to preserve these instances. And like I mentioned, that's not common in mammals. Morgan et al., 2009, point out that the howler monkey comparison, which I made earlier, suggests the potential for loud vocalization in these oreodonts, and there's similar potential in Panoptis. However, much more study of modern mammal tracheal anatomy and vocalization is really needed to say anything concrete. Now, I couldn't pass up the chance to talk about this bizarre find from recently. So, bones previously thought to be the hyoids have actually been re-identified as an ossified larynx in two Asian ankylosaurs, Panachosaurus and Sichania. This makes them the oldest known larynxes in the fossil record. And they are bizarre. They're strikingly bird-like in some respects, such as a fold down the middle, sort of a hinge that things other than birds don't really have. Now, there's no soft tissue present to tell whether they would have had vocal cords there, as modern reptiles would vocalize with outside birds. While this is not necessarily indicative of a second vocal organ on their own, ankylosaurs were clearly doing something very strange vocally. For now, let's move on to the syrinx. The syrinx is a separate vocal organ from the larynx completely, and is entirely unique to birds. It's located at the base of the trachea, above the lungs. And across birds, there is extreme anatomical diversity in this structure, in the tracheal rings, in the soft tissue anatomy, many different things. And this is correlated to high diversity in call types and vocalizations within birds. Think all of the singing and booming and quacking and hooting they do. Now, these can have one sound source vibrating just above the tracheobronchial juncture that you can see on the right there, or it can be two, below the TBJ, down closer to the lungs. Two sound sources allow some birds to even harmonize with themselves, which is that bifinition we talked about earlier. And this allows them to do some fascinating things vocally. But along with the ankylosaur larynx, which is strikingly bird-like, this is probably making you wonder how long ago the syrinx arose. So we look to the fossil record, and we do occasionally get fossilized syrinxes. For instance, in Presbyornis, an extinct anseriform, which generally resembles other anseriform syrinxes like magpie goose, with similar fusion of rings, although it lacks asymmetry as in some other ducks and geese and such. We also have Yayawavis, which is a forest rockid from the Pliocene. And we actually have a full-on preserved trachea and syrinx in this guy. It's only briefly described and only sort of figured, but it appears to have little fusion or asymmetry in the rings. And an analysis of the inner ear of Yayawavis and another forest rocket, Patagoras, suggests they were tuned for hearing low frequency sounds. Now, this is consistent with forest rockets' general large body size, as in general in animals, as body size increases, fundamental frequency decreases. Now, we have one more fossilized syrinx, and this is the oldest one, from a stemanceriform from the late Cretaceous of Antarctica called the Vagabus. Now, this is found fairly complete and three-dimensionally preserved, with slight asymmetry just above the tracheobronchial junction. And this is amazing. This is a Cretaceous vocal organ. But there's just one problem for using it to interpret everything about syrinx evolution. This is a neognath bird. Now, if you look on the far right there, neognaths are one of the two main clades of birds alive today, along with paleognaths. But we already know, based on paleognaths, that syrinxes are at least ancestral to birds, if not earlier. The problem with this is we don't know what happened between earlier archosaurs, like pseudosutians, crocodilians, and everything in between there. And this presents us with a mystery. We have two hypotheses about how the syrinx actually arose. The silent period hypothesis, in which some avametatarsalиans lost vocal function of their larynx, but actually retained the larynx itself. And later on, a new vocal organ evolved, the syrinx. Good thing to note here, this does not mean that these lineages were entirely silent. As discussed before, there are many different ways to make sounds. We talked about mechanical sounds, but there's also hissing and other things that don't require as much vibration. There's also the functional overlap hypothesis. And in this hypothesis, some avametatarsalиans evolved the syrinx, which was used alongside the larynx in order to vocalize. Then vocal production in the larynx was lost, although it could still modify sound as in birds. Now, we don't have a full answer to this question, unfortunately. We'll have to see as the fossil record hopefully produces more syrinxes going forward, farther and farther down the tree. And that is kind of the end of that story for now. So before I go, I want to talk a little bit about resonating chambers and elongation of the vocal tract and how that affects sound production. So there are a lot of animals that do this. Lengthening the amount of tube that sound has to travel through lowers your fundamental frequency. And this is shown in things like this saiga antelope on the bottom right, which uses muscles to extend its nose and lengthen the vocal tract. Same thing in this hooded seal on the right here, which inflates its nose and resonates sound in the nose. And so birds also do this with their trachea, and all of this elongating and creating resonating chambers can be used to make an animal sound bigger. Remember the trend of body size with fundamental frequency being inverse. Lower sounds are produced by bigger animals. However, in terms of the fossil record, there is one really famous group that has been hypothesized to have done this, and that's lambeosaurs. One of the leading hypotheses for the extravagant crests that lambeosaurs have is that these nasal tubes that run all the way through these crests that they've been CT scanned and looked at the inside of were used to resonate sound and elongate the vocal tract. And this would lower the frequency substantially of sounds that they were making for already large animals. We're talking about estimated frequencies of 50 to 60 hertz, probably lower. Although soft tissue would certainly play a big role in sound production, these bony nasal passages offer a rare glimpse into potential sounds made by non-avian dinosaurs that we don't normally get, given our lack of vocal organs in them. So let's zoom out and look at the big picture real quick. We've talked about a lot of these events here, but early in the Paleozoic, aquatic invertebrates and fish were likely producing mechanical sounds and swim bladder drumming long before tetrapods ever got on the scene to make noise. During the early Permian, you get multiple different origins of the tympanic ear in tetrapods, which allowed them to hear through air better. And shortly after that, the gunshot was off, and we were off to the races for sound production in tetrapods. We had all sorts of bizarre adaptations to making sounds, whether it be in invertebrates out in katydids that we talked about earlier, archosaurs and their larynxes, and at some point the origin of the syrinx, or the resonance aspect in the display structures of lambeosaurs. And this all comes together to show that the sounds of deep time were not static. These were very much ever changing through deep time, just like any other structure. I hope this gave you a little bit of an insight into how various different soundscapes would have been filled with many different sounds, some of them that we're used to, some things that we're not used to through deep time. So thank you, and feel free to leave me questions in the Q&A channel. I hope to see you all soon. Bye-bye.